Okay, so the question says, imagine a package of flower seeds contains an equal amount of 6 types of seeds, and then it lists them off. It says you'll plant your seed in one of 4 locations. List those 4 locations. How could you design an experiment to choose a type of flower seed and where you would plant it? So what I've done is I've gone ahead and looked at the probabilities for this, which I'll show you in a second. This is going to guide you through this with some questions. So the first one it says is, which flower seed would you most like to plant? And what is the probability of attaining that seed? So what we're really doing here is we're going through the theoretical and also then the experimental probability. So the theoretical deals with, in theory, what should happen. So what's the probability of attaining whatever seed we want? Well, there's 6 seeds that are equally as likely to be obtained. So chances of us getting the one that we want is 1 in 6. Next it says, where would you like to plant the seed? If the location is randomly selected for you, what's the probability of getting the location you want? Well, no matter which one we select, like here, I didn't say which one I wanted, it doesn't really matter. For the second part here, it is going to be 1 out of 4 possible locations. So for the first one, we have a 1 in 6 chance of getting the flower that we want. For location, we have a 1 in 4 chance of getting location. So it says, what do you think is the probability of getting the seed you want and the location that you want? Well, to see that, I've actually created a little table here. I'll show you. So we've got location across the top, 4 different locations. We've got seed type across the side, and I've created this table for us to see all the different options. So if we look at this here, in total, there are 4 options for location, 6 options for seed type, 6 and 4. So there are 24 different possibilities. Now we're looking for just one of those, whichever it is. So I didn't say before what we wanted. So let's say that we wanted Daisy, and we wanted it to be at, well, actually just in a flower pot. So I need to look for that combination here. So Daisy in a flower pot is actually the last one that I have here. Don't worry about the numbers yet, but just note that it is 1 out of 24 options. So what is the probability of getting the seed you want and the location? 1 out of 24, which note is the same thing as 1 over 6 times 1 over 4. So it says design a simulation to show the probability of obtaining each of the 6 seed outcomes and the 4 location outcomes. So there's a bit of a difference between a similarity and using a table or fractions for this. So let's point out the different things. This is a table. Obviously, we saw that from last time. This other aspect, this way that I've done that, is by way of using fractions. That's what this lesson goes through, much more so. It's called determine probabilities using fractions. So that's what you're just discovering today. And then there's also simulations that you can run, which is the experimental probability aspect to it, because they want you to actually run an experiment. So let's just skip ahead for 1 second here. It says design a simulation. I'll show you that in a sec. It says experiment by running your simulation until you get your desired outcome. How many times do you need to run the experiment? And it says how do your experimental results compare to the theoretical probability of getting your desired outcome? So what I'm going to do is I'm going to show you the experiment that we're going to run, and it's going to help us to see how long it takes for us to get what we'd like, which is a daisy in a flower pot. So 6 and 4. So what I have here, simply from Googling roll a die, I came across a random number generator here that we can use. So the first die, the square one here, shows the numbers 1 to 6. We can see right there it shows 6-sided die. The other one is a 4-sided die, and what I can do is I can roll these in combination. As a reminder, and if you can see it from my table, the blue refers to the seed type. The green refers to the location. So we're looking for a blue 6 and a green 4. And we're going to see how many times it takes us to do this. And I'll try to do this quite fast. All right, so let's start rolling. Okay, so it's not going to be nearly as fast. So what I'll do is I'll just sort of cut over to telling you guys how many times it did it. Because that's the second time, third time, fourth time, fifth time, sixth time, no, seventh time, eighth time, Okay, so I'll cut across and well, I'll pause it and let you guys know what I get to. That's the ninth one right there. Okay, so it was actually on my 12th roll, so not that much after I sort of paused it for you guys to save you from just hearing me count. So on the 10th roll, we got 6, 4. That's going to be the answer for the question within this section of the quiz, that it took 12 rolls to get there. But I'm going to encourage you guys in a moment to also try this yourself and see how long it's going to take. Okay, so we did these aspects to it. We designed a simulation to see how long it would take to get our desired outcome. We ran that experiment, and it took 12 tries. So the last question here says, how do your experimental results compare with the theoretical probability of getting your desired outcome? Well, it was actually, twice as fast to get it. We expected that it would take 24 tries, or that'd be 1 out of 24. And that's what's going to happen over time. So if we were to run this simulation again, seeing how long it would take us to get the combination 6, 4, the first time it took 12. I'm actually going to run I guess 2 more simulations here just to show that it's going to vary over time with this. And I'll just let you know what those numbers are. All right, so believe it or not, these are the numbers for the amount of tries it took me for my next few attempts. It's actually took me a little while here to get a bit of a range with this. So next time it actually took exactly 24. And then it was really quick, only 5, and then 9, and then 10. Really showing that the experimental probability with a few tries was much less than the theoretical probability. We expected it should take like once every 24 times because there's 24 different options. It should be the flower pot and the daisy, but it was happening much faster. And then it started evening out over time. So the next trial took 28, and then astonishingly, probably more astonishingly, that I actually clicked through this number of times to get there, that I didn't just give up and make up a number. Believe me on this. It took me exactly 100 tries on the last one just to get that. So very much evened out over that time. If we were to average this, so knowing what we know about averages now, mean, median, mode, and so on, average these out, and let's see what we get. If I add up each of those values and I divide by how many values we have there, so we know that's how we calculate the mean or the average, as we call it, you're going to get approximately 27. So based on our number of trials that we did here, after one trial, our experimental probability was 12. But I mean, one simulation for that really doesn't give us a good understanding of what it is. You need to do multiple trials for that. So as we did more trials, we realized that we were getting closer to, well, it should eventually get to 24, and we were at 27 there. So imagine if instead of doing 7 trials, we did 100 trials where we rolled the die as many times until we got our desired result. This number should get closer and closer to 24 over time, which is our theoretical probability. It's the same idea that if you flip a coin 100 times, then you're expecting to get 50 heads and 50 tails, and it might not work out exactly that way, but over time, so instead of doing it 100 times, you do it 1,000 times. You should get closer and closer to that middle split value on it. So anyways, just to sort of explore theoretical and experimental probability a little bit. 1 out of 24 is the theoretical probability of getting what we wanted, the daisy in the flower pot. And then experimentally, over a number of trials, we saw that it takes approximately, well, the probability is 1 in 27 there. But like I said, the more trials that we do, the closer it's going to get down to that 1 over 24.